Okay, good morning, guys. So today we're going to pick up where we left off last time. Last time we introduced arc length, and I mentioned that our next stop was surface area. So today we're going to start talking a little bit about surface area, which is section 8.2. Sorry. Okay. Here we go. Okay. So we're going to look at solids of revolution and see how to calculate their surface areas. And this is thankfully pretty intuitive, but the calculations can be a little bit difficult. And they do involve something similar to the arc length calculations. So let's take a look. So imagine you have some function here, f of x. And if you rotate the region between A and B, here we'll just assume we're going to rotate about the x-axis. This generates a solid, right? In this case, it's going to generate a solid that kind of looks like this. All right. I'm sure you guys have some amount of PTSD from back when we worked on these solids of revolution. So hopefully this isn't too hard to remember. You can picture that solid a little bit, right? It's kind of like a flower vase or something like that. The idea here is if we want to find the surface area of this solid, what we should do is take a little bit of the arc length along the way and rotate that. So imagine you take some little stretch of arc length here. And rotate just that bit of arc length, then that would generate a little patch of surface area. And if we imagine that that little stretch of arc length is short enough, so we'll call this little stretch of arc length. The normal notation here is ds. I'll explain. This is your little stretch of arc length. Then I'd like to see if we can find this bit of surface area. And you have to kind of imagine similar to what we did for the cylindrical shells method of volume. You know, you can think of this as being an extremely thin cylindrical shell. So how do you think we could find the area of this little patch of surface here? Well, I can like cut and unroll it, similar to how we would have done for the cylindrical shells method. And it will cut and unroll into a strip. Where this is still ds, our little arc length bit, and this is something else. Hammy, be good. Remember, as this thing sits on the axis, on the x-axis there, if you were to look at it from straight on like this, or from straight on like this, you would be seeing a circle, and that circle has a radius. That radius is determined by this distance here, right? The distance from the horizontal axis, or the axis of rotation, to the function at the point where you're looking at this little ds arc length strip. Which means that this radius is equal to f of x. Right, if we're stopping here at a particular x value to draw this little patch, then that vertical distance, the distance from the horizontal axis, the axis of rotation, all the way up to the curve where this patch is taking place, is the height of the function here, because this point is x comma f of x. So that means this distance right here is the circumference, which is 2 pi times f of x. Which means that this little patch of surface area, which I'll call dA, is 2 pi f of x ds. And now it's just on us to figure out what ds is. But we know what ds is. Your little piece of arc length, remember, I'll use the symbol s. From x equals a to x equals b is s equals integral a to b square root of f primed of x squared plus 1. This is what we were doing last time, times dx. That's no bitch. Right? This was our arc length formula. And I'm going to go ahead and use the symbol S for arc length. This is the normal notation that every differential geometry book uses. So ds is the little differential amount of arc length that we're integrating to get S here. So ds is the square root of f primed of x squared plus 1 times dx. So the last thing I have to do is take that ds that represents this little distance here and plug it into my formula here. So dA, my little differential surface area, is 2 pi f of x times the square root of f primed of x squared plus 1 times dx. And that means that surface area is going to be found by integrating this thing. We'll integrate from a to b 2 pi f of x times the square root of f primed of x squared plus 1 dx. And that's the game. Now, sometimes these integrals are easy to handle. Sometimes these integrals are very hard to handle. A neat fact is that a lot of the things for which the arc length integral is very hard, the surface area integral is manageable. If you're lucky, the kind of piece that you would need to substitute in this integral, but you can't substitute because you don't have it, is exactly the f of x piece here. So sometimes this gives you a little something extra to play with that you don't have in the arc length setting. In other words, there are curves where I can't compute the arc length, but I can compute the surface area, and that's kind of neat. There are also some really surprising examples here when you compare surface area to volume. One of the nice intuitions that people who work with physical objects a lot like to talk about is how mass scales with the cube and area scales with the square. So as an object gets bigger and bigger, its mass and its volume kind of get larger on order 3, right? They get larger kind of with the cube of the length. Whereas surface area gets larger according to order 2. Surface area sort of scales with the square of the length. Now, of course, objects like these don't have a defined length, right? They're different sizes and all sorts of different dimensions, but that's an intuition that's nice to have. So the surface area tends to be a little bit smaller than the volume. Tends to be an order of magnitude smaller than the volume, in fact. So up here in the top right, this is the formula from last time. Down here in the bottom right, this is the new formula for today. And it's just a neat fact that the surface area and arc length formulas are sort of linked together. So I'd like to take a look at an example or two. Unfortunately, these are not cases where I can come up with examples readily on the fly, because if you start writing these things down at random, odds are the integral will not be manageable. So here's the sort of picture we're looking at, right? This pink is the arc length, this blue would be the volume. You take a little element of the arc length and rotate it, and that will give you this thing. And these are all going to be swapped out for differentials when we send n to infinity. And you get the result that we have here. So for fun, let's take a look. There's a few other notations you could use here. I don't recognize it. I don't suggest that you burn space in your brain memorizing these. Let's take a look at an explicit example. Yeah, okay. So we're going to look at this curve from -1 to 1. And we're going to rotate it about the x-axis. Then we're going to find the surface area of that portion of the sphere. So we're going to find the surface area of the solid generated by rotating the curve of the region bounded by y equals the square root of 4 minus x squared from x equals -1 to x equals +1 about the x-axis. And as the book points out, if you square both sides of this equation and rearrange it, you'll see that that is the same as x squared plus y squared equals 4. So the thing we're playing with here is a sphere of radius 2, or the object we're beginning with is a part of a circle of radius 2. So my art is bad and I feel bad. But we just want to take the piece that's from -1 to 1. So up here, this would be the point 0, 2. And really, we're just looking at rotating this piece. So I know I marked these, and now it looks like this, but this would be 1. Over here, -1. So I want to rotate this region. When I rotate that region, what I'm going to get is going to look kind of like a fat wedding band. Can you guys all picture that solid? If I rotate that shaded region about like this. Okay. So here's my function f of x. In order to calculate the surface area, first I need to calculate the little ds, the little arc length differential. So ds is the square root of f primed of x squared plus 1 times dx. So I'll need f primed. F primed is the derivative of this, which is 4 minus x squared to the 1/2 power. I want to be clear, we can't give this 1/2 power to these things separately before we differentiate. Same as you can't distribute that square root before you differentiate. The algebra just doesn't work that way, right? But what we can do is apply the power and chain rule here to get our derivative. So this will be 1/2 times 4 minus x squared to the -1/2. And then by the chain rule, we multiply by the derivative of the inside, which is -2x. So the 2's and the 1/2's will cancel. And here I get -x times 1 over the square root of 4 minus x squared. This piece is the 1 over the square root. This piece and this piece, the 2's cancel, and you're just left with the -x. So ds is the square root of this squared plus 1. Maybe I'll rewrite this as -x over the square root of 4 minus x squared, just to make it a little bit easier to plug into this formula. So I'll have the square root of f primed of x squared plus 1 which is the square root of this squared plus 1 times dx, sorry, times dx. And when I square this, the top will be x squared, the bottom will be just 4 minus x squared, and the negative will go away. So I'll have here x squared over 4 minus x squared plus 1 times dx, which means that my integral for the surface area will be the integral from -1 to 1. Remember, it's 2 pi f of x times ds. That's the recipe. ds is this little arc length element that we just cooked up and simplified. And f of x is this function that we started with. So this is 2 pi integral from -1 to 1 square root of 4 minus x squared times ds, which is the square root of x squared over 4 minus x squared plus 1 dx. So this is the integral we need to handle, and it is a little bit intimidating. It's a product of two kind of nasty square roots. Each one looks like it would be something I'd be kind of afraid to integrate on its own. This guy, if I had to integrate it on its own, I could. That's a little bit of trig sub. Over here, I'm not even sure if I had to integrate this on its own, what I would do at the start. But I would probably begin by having a common denominator and trying to clean things up. In this case, because I have those two pieces multiplied, I'm going to begin by writing them as one big square root, and the inside will be this times this. So I'm going to have one big ass square root. Inside that big ass square root, I'll have 4 minus x squared times x squared over 4 minus x squared plus 1. Right. Now, if you take this thing as a single chunk and distribute it over this thing, thinking of this as a chunk and this as a chunk and this whole parenthetical here as a chunk, I'll get 2 pi times the integral from -1 to 1, 4 minus x squared times x squared over 4 minus x squared. The 4 minus x squareds will cancel. And from that piece, I'll just get x squared. And then 4 minus x squared times 1 is just going to be this. You can think of these as being in parentheses if you want, but they're being added. So it doesn't really matter. And the miracle here, of course, is that the x squareds go away. This function turns out to be constant. This is 2 pi times the integral from -1 to 1, x squared plus 4 minus x squared. That's just the square root of 4. So this is 2. I can pop the 2 out and I get 4 pi integral -1 to 1 of dx. And the integral from -1 to 1 of dx is just 2. Right, your antiderivative there is just x. We can write it out. This is 4 pi times x evaluated from -1 to 1, which is 4 pi times 1 minus -1, which is 4 pi times 2, or 8 pi. So this particular calculation was not bad at all, because of the way the algebra from f of x and the algebra from ds interact with each other. And who would have guessed at the start that this would be so nice? Of course, it's not always this nice. Questions on this? So there's kind of a lot to do on these. But the good news is that they're fairly formulaic. I'm not trying to shake you to your core with these problems. I want you to understand the concepts. So I'm not going to bombard you with situations where you have to work with weird axes of rotation. Your axis of rotation will always either be the x-axis or the y-axis, usually just the x-axis. I won't be as harsh on these as I was with the area and volume problems at the beginning of the term. Because frankly, you've got enough to do here. Last call for questions on this example. Okay, so this is a nifty problem. Here's what your solid looked like, right? Kind of like a wedding band. It's a sphere with the sides chopped off. See, I would like to do the Gabriel's horn example. We should do a scary one, I guess. Yeah, e to the x from 0 to 1 about the x-axis. Let's try one of these that looks a little bit more intimidating. And then I have a really fun example to show you called Gabriel's horn, but it's going to be just a second. So here, let's find the surface area of the solid generated by rotating the region bounded by y equals e to the x from x equals 0 to x equals 1 about the x-axis. We'll be looking at these same problems from the perspective of parametric curves next week. For now, we know how to draw this graph, e to the x. That's not a difficult one. It looks like this. All right, he approaches y equals 0 on this side. He blows up to infinity on this side. And I'm interested in the space from 0. Let's call this 1 here. And we're going to rotate that about the x-axis. I'm going to take this region, rotate about the x-axis. You can kind of picture that solid. I'll do my best to help out here. right? Viewed from the side, this kind of looks like a little horn, doesn't it? And what I would like to do is find the surface area. To find the surface area, we need ds. ds is the square root of f primed of x squared plus 1 times dx. And again, I want you to remember that this ds stands for a little tiny element of arc length. That's taken at position x. That's the way to think of it. So we're thinking of this surface area as coming from rotating this tiny little piece of arc length. Because when you rotate that tiny little piece of arc length, you get this tiny little band of surface area. And if you were to add up all of those tiny little bands of surface area, that would give you the whole surface area. That's the nice thing here. So here, f of x is e to the x, which means f primed is e to the x, which means this is e to the x squared plus 1 under my square root times dx. So my surface area is going to be the integral from 0 to 1 of 2 pi f of x ds, which is 2 pi integral 0 to 1 e to the x times the square root of e to the x squared plus 1 dx. E to the x all squared so this integral is the one I'm continuing over here. E to the x all squared under the square root. Let's see what that looks like. That's integral 0 to 1 e to the x times the square root of. Actually, you know what? I was going to write this as e to the 2x, and we can, but because of what we need to do here, I'm just going to leave it as e to the x squared, like that. What's the move here? How do I do this integral? So in my brain right away, I was thinking, well, I should write this as e to the 2x because it's e to the x all to the 2, which is the same as e to the x times 2. But because of the particular move that I'm going to make, yeah, we should make a little substitution. I'm going to let z be what? Yeah, e to the x. Very good. That'll get rid of the e to the x here, and this piece will soak up the differential. Because dz would be e to the x dx. I also need to change my bounds. Anytime I do a substitution, I change my bounds. So when x is equal to 0, z will be equal to e to the 0, which is 1. And when x is equal to 1, z will be equal to e to the 1, which is e. So then this integral is going to become 2 pi integral from 1 to e. This e to the x and this dx make up dz. This piece will be square root of z squared plus 1. So this is where we land. And how do I do that integral? Is that the same as z plus 1? Say it loudly and proudly. Yeah, no, it's not. Right, definitely not. But we can use trig sub. What kind of substitution do I need here? Sine, secant, or tangent? Good, yeah, this is a substitution for tangent. I should let z equal tan theta. Right, and if you don't remember this, look back at your trig sub Bible from before exam 1. Here you've got your variable squared plus some constant. A here is always the square root of this constant. This constant is 1, so z equals a tan theta. Z equals 1 tan theta here, which means dz is secant squared theta d theta. And again, we need to change our bounds. When z is equal to 1, you'll have 1 equals tan theta. So theta is the inverse tangent of 1. That's pi over 4. But the upper bound is less nice. When z is equal to e, theta is just going to be, theta is just going to be the inverse tangent of e. And there's really not much we can do with that. Just leave it as what it is. So we can plug these things into our integral. And I'll have 2 pi integral from pi over 4 to the inverse tangent of e. My square root is the square root of tan squared theta plus 1, because that z is tan theta. So z squared is tan squared theta. And dz is secant squared theta d theta. I don't know if you guys remember what these look like, but if you start off with a square root like this, square root of x squared plus 1 or square root of z squared plus 1, that always becomes the ever favorite, always intimidating secant cubed integral. Tan squared plus 1 here is secant squared. The square root of secant squared is secant. So this is secant times secant squared. So that's the integral from pi over 4 to the inverse tangent of e secant cubed theta d theta. Who remembers how to do the integral of secant cubed? So we're getting a nice refresher on all of our tricky integrals from the beginning of the semester. It is a looping integral. Yeah, Maggie's correct. You use IBP once. U here, you split this, you think of this as secant times secant squared. U here is taken to be secant theta, and dv is taken to be secant squared theta d theta. I'm not going to show the full IBP here, but this is an IBP, and then it loops, takes one run of IBP, and what you'll get is that the integral of secant cubed is 1/2, so we'll get an over 2 up front here, secant theta tangent theta plus the natural log of secant theta plus tangent theta. So we need to evaluate that from pi over 4 up to the inverse tangent of e. Oh, I need to close this absolute value. So the 1/2 from the integral that I get that comes from the looping will cancel with the 2 and the 2 pi. And then I need to evaluate this between these bounds. I'm going to move the page up. If I plug in my upper bound, I have the secant of the inverse tangent of E times the tangent of the inverse tangent of E plus the natural log of absolute value of secant inverse tangent E plus tangent inverse tangent E. And then from that, I have to subtract what I get when I plug in pi over 4. The secant of pi over 4 and the tangent of pi over 4 are not hard to sort out. Tangent pi over 4 is 1. Think about your unit circle for all this. Tangent of pi over 4 is 1. What's the secant of pi over 4? What's the cosine of pi over 4? Yeah, good. The cosine of pi over 4 is root 2 over 2. So the secant of pi over 4 is 2 over the square root of 2, which is just the square root of 2. I'll write it like this for now, but I think it's worthwhile to get into your brain. Root 2 over 2, that number that you deal with so much in the unit circle, it's just the reciprocal of root 2. It's 1 over root 2. It's being rewritten with a rational denominator. So for now, I'll write it like this. We have this times 1, and the tangent, plus the natural log of the absolute value of this plus 1. And then we can close our bracket. So we've got some work to do. I'd like to figure out what this is. First, let me just put this all in one line. So I have secant of arctan of E. The tangent of the inverse tangent of E is just E, plus the natural log of the secant of the inverse tangent of E, plus, again, tan of arctan E, that's just E. And then from that, I need to subtract 2 over root 2, which is just root 2. And when I distribute this, I also need to subtract the natural log of 2 over root 2, which again is just root 2, plus 1. So here's my answer. It's correct, but it's not as nice as it could be written. In particular, I would like to know what this is. It shows up twice here. And the trick to doing that is to draw a little triangle. You're going to label this, and I want to simplify the secant of the inverse tangent of E. First, the inside, call that some variable, phi. I like to use a Greek letter because it's an angle, and I don't want to use theta because I used theta to mean something earlier. Oh, I lost a pi, didn't I? Thank you. Yeah. The 2's canceled, but the pi's did not. So there should be a pi in front of all of this. Should be a pi in front of all of this. Thank you. Thank you. Thank you. Yes, you're 100% correct, Zach. Okay, so coming back to this, that means that the tangent of phi is E. And E is the same as E over 1. So I can draw a little triangle, a little right triangle where the internal angle here is phi. And the tangent of that angle is E over 1. So that means the opposite side here is E and the adjacent side here is 1. I draw this just from the fact that tangent of phi is E over 1. And now remember what I want. The secant of the inverse tangent of E, that's just the secant of phi. So if I complete this triangle, I can read off the secant. I know that this squared plus this squared has to be this squared. So this guy is the square root of E squared plus 1. And so the secant of phi, which is the thing that I want, is the reciprocal of the cosine of phi. Cosine of phi would be the adjacent over the hypotenuse. So this is the hypotenuse over the adjacent. This is the square root of E squared plus 1 divided by 1, or just the square root of E squared plus 1. So that is this piece and this piece. So altogether, I find that my surface area is pi times this, which is the square root of E squared plus 1, times E, plus the natural log of the square root of E squared plus 1 plus E, minus the square root of 2 minus the natural log of the square root of 2 plus 1. And that's the game here. These guys are being multiplied. It's a little bit gnarly. It's a little bit gnarly, right? Here we had to do U sub and then trig sub. And then if we didn't remember the secant cubed integral, you have to do a looping IBP. Then you evaluate to this mess, and this mess requires some careful trigonometry to simplify. And even once simplified, let's be honest, it's not pretty. Could you simplify this a little bit more? Well, maybe. I mean, you can get rid of the absolute values in the log because these things are positive. And then you could combine the two logs as one log with this over this inside using properties of logarithms, but that's not going to get much nicer because there's no simplification you can do inside the log. So I would say this is about as nice as this is going to get. It's a complicated and scary looking answer, but them's just the facts. Is there any piece of this that you guys would like to look out more carefully? Okay, if there are no questions, I'm going to move on to my last example here for today, which is a fun example. It actually has to do with improper integrals. And this is something I remember. So when I was in undergrad, specifically when I was at community college, I was working at this little health food store. And I remember one day running in there so excited, yelling at my coworkers who obviously couldn't give less of a shit, that there are objects in this existence that have infinite length but finite volume. There are objects in this world that have infinite length but finite surface area. And there are some objects in this world where the length is infinite and one of the volume and surface area is infinite but not the other, which leads to a kind of weird paradox if you think about it. So rather than spoiling the surprise for you, I want to set up the problem and let us discover it together. Just like the solid from that last one kind of looked like a horn, there is a famous horn-shaped problem. Gabriel's horn is the solid generated by revolving the region bounded by y equals 1 over x from x equals 1 to infinity about the x-axis. And I'd like to ask two questions. Is the volume of Gabriel's horn finite? And is the surface area, SA standing for surface area of Gabriel's horn, finite? So before we can dig into this, I'd like to draw the picture for you. There's nothing too radical about the picture. We all know what 1 over x looks like. One over x looks like this. And we're going to take this thing from 1 all the way out to infinity. So if you try to picture what this solid looks like, goes on and on and on forever like that. The reason it has the name Gabriel's horn is coming from Christian theology. Gabriel, I think, was like an angel or something. And I think Gabriel's horn is supposed to be a signifier of the apocalypse or something frightening like that. I'm not too sure. Some infamy in Christian theology around the horn of this angel Gabriel. And the catch here, of course, is that because this thing goes on and on and on forever, b, the upper bound in all of your integrals, is infinity, which means that they're improper integrals. So from the mathematics standpoint, this gets interesting because it blends the convergent stuff with the volume and surface area stuff. So first, let's take a look at the volume. I can do this using the disk washer method. If x is here, I imagine my little strip looking like this. The dV that I need for the volume is pi times r squared dx. And r here is the distance from the axis of rotation to the far end of my strip. So this is pi times, there's really only one r here, right? I think we were using capital R for this earlier. So this would be pi times 1 over x all squared times dx, which means that the volume itself is going to be the integral from 1 to infinity of dV, which is the integral from 1 to infinity I can pop out the pi. 1 over x all squared is 1 over x squared dx. And we recognize this right away as a p integral, right? And this is a constant multiple of a p integral. So I know that it will be convergent, but just for fun, remind ourselves how to set these up. There was some issue on the test where people got sloppy and didn't write their limits when they did these improper integrals, all sorts of things. So I just want to run through one of these. Carefully and correctly. Your antiderivative for x to the negative 2. You add 1 to the power, that's going to be x to the negative 1. And then you divide by that new power. So this is going to be negative 1 over x, evaluated from 1 to r. Oh, and we still have our limit out front. So that will be pi lim r to infinity, negative 1 over r minus negative 1 over 1, which is pi times 0 plus 1, which is pi. So the volume of Gabriel's horn, the amount of stuff it takes to fill Gabriel's horn, is finite. Right? The integral that represents the volume, the improper integral that represents the volume, is convergent. So, for example, if you had a big can of paint, you could fill Gabriel's horn, right? Just turn it up on its side, plug the bottom, and fill it. It takes this much paint, pi, to fill that thing. What if you wanted to paint the outside? How much surface area does Gabriel's horn have? Well, here, remember that the surface area is the integral from a to b, 2 pi f of x times ds, where ds is the square root of f primed squared plus 1 times dx. So ds here, I take the derivative of 1 over x. The derivative of 1 over x is negative 1 over x squared. Right? F of x is 1 over x, which means f primed of x is negative 1 over x squared. That's a power rule derivative. So the piece that goes in here is negative 1 over x squared plus 1 dx. And that means that my surface area A is the integral from 1 to infinity 2 pi f of x, which is 1 over x, times this square root, which is negative 1 over x squared plus 1 dx. And if you're thinking that this integral looks intimidating, boy, are you right. My first step here would be to pop out the 2 pi and write what's left over as a limit, lim r to infinity, integral 1 to r, 1 over x times square root of, if you square this, you'll get 1 over x to the 4 plus 1 dx. All right, this would be my first step if I was going to compute the integral. The integral here is not easy. Be clear about that. You can have a common denominator between these pieces and write it as 1 plus x to the 4 over x to the 4. You can give the square root to the top and bottom separately, and you'd end up with the square root of 1 plus x to the 4 over x cubed, because you'll have a square root of x to the 4 from the radical piece and another x downstairs from this piece. But this is not an easy integral to compute. It is, however, an easy integral to get the convergence result for. Let me move the page up. This is hard to work with directly. So what I'm going to do instead is use my comparison theorem for improper integrals. This object is bigger than 1. Because in this square root, you're taking 1 and adding something positive to it. This is true for all x bigger than 0, and definitely true for all x is bigger than 1, which is what I need. And this means oh wait, let's see, is this gonna, yeah, this will work. This means that this inequality is true. Which means that the integral of this has to be bigger than the integral of this. So the integral from 1 to infinity of 1 over x dx is less than or equal to the integral from 1 to infinity of this, which is the thing I'm trying to do. And since the smaller integral diverges, it's a p integral. With p equal to 1, which is not bigger than 1, it follows from this inequality, we'll call it star, from star and the comparison theorem, right? My integral is bigger than this divergent integral. So it follows from the comparison theorem that the surface area integral diverges also. In other words, the surface area of Gabriel's horn is infinite. So how's that for strange? You have here an object that you could fill with a finite amount of paint, but that very same amount of paint is not enough to coat the surface, at least with a uniform thickness. You have an object here with finite volume, but infinite surface area. And this is mind-blowing. It contradicts so many things, including that thing I told you at the very start of class, that usually volume scales with the cube and surface area scales with the square. Usually volume is an order of magnitude larger than the surface area. But here it's the other way around. The surface area is infinite, the volume is finite. So can you imagine having a physical object like a coffee cup that you could fill up with some amount of paint, but then that isn't enough paint to coat the surface? It just doesn't make sense. It's very counterintuitive. And this is just one of the many, many, many things that are counterintuitive when you start playing around with infinities. Of course, it's not the first time we've seen something like that. Something surprising coming up in this situation where you're dealing with convergence. But this is a particularly fun example. Of course, everything we've done on this page isn't directly related to surface area. This is all about convergence. So the surface area work itself was all done back here. So are there any questions on the surface area setup? Any questions on how we got this integral? Okay, then you guys are free for the week. I've got a few minutes left to play here, so I would like to kind of get your brains ready for what I'm going to show you next week, because it's conceptually a little bit challenging. What we've done here with surface areas and arc lengths, I don't think is all that hard to like reason your way through. But what we're about to do is something that for most people in Calc 2 is totally new. So the next thing we're going to talk about sort of the last two topics for this class are parametric curves and polar coordinates. Oh yeah. So the final lines there. Was, here. So this inequality is where we began our comparison. I observed that the thing under the square root here is bigger than 1 because I'm taking something positive and then adding 1 to it. If you take the square root of something that's bigger than 1, well, the square root of 1 is 1, so the square root of something bigger than 1 has to be itself bigger than 1. That's the jumping off point. Noticing that this square root, no matter what x you plug in, is going to be bigger than 1. Then we multiply through by 1 over x. 1 times 1 over x is 1 over x. This square root times 1 over x is this. And the 0 is just here as an observation, because remember, for the comparison theorem, we need everything to be bigger than 0. And it is true that as long as x is positive, 1 over x is bigger than 0. And by the line above, 1 over x is smaller than my integrand, which means that my integral is larger than the integral of 1 over x, since the integral of 1 over x from 1 to infinity diverges. It follows from the inequality that my integral diverges also. That integral was a surface area, so the surface area integral diverges, and that means that the surface area of Gabriel's horn is not finite, it's infinite. Okay, so I do want to introduce this material a little bit. We're used to seeing curves like y equals f of x, or sometimes x equals f of y. right? Like y equals e to the x, or maybe x equals 1 minus y squared. Stuff like this we're all familiar with. A parametric curve, though, is one where x and y are independent of each other, but both dependent on another variable t. So like x equals t and y equals 1 minus t. And maybe I specify a domain for t. -1 is less than or equal to t is less than or equal to 1. Shit, just for fun, let me make this t squared. Why not? So this would be a set of parametric equations. X equals t squared, y equals 1 minus t, where t runs from -1 to 1. In this particular case, I can make a table of values to try and graph this. When t is -1, x is t squared, that's 1, and y is 1 minus t. 1 minus -1 is 2. So this graph, it doesn't have a t-axis. It's normal. It's just x and y. So you can't see the independent variable anywhere in the graph. But I know that when t is -1, which is my smallest t value, I'm at the point 1, 2. So this is where my curve starts. When t is equal to 0, x is 0 squared, and y is 1 minus 0, that's 1. So I would be at the point 0, 1, 1, 2, 0, 1, which is right here. And when x is equal to +1, when t is equal to +1, x is equal to t squared, and y is equal to 1 minus t. 1 minus 1 is 0. So that puts me at the point 1, 0. It turns out that this curve is actually a parabola. It's sideways. And if t is just allowed to run from -1 to 1, then I would just have this piece. And it's traversed with a direction. We started up there, and then we came over here. So this would be called my initial point, and this would be called my end point or terminal point. So this business of expressing a curve in the plane, rather than with y as a function of x or x as a function of y, we let both x and y be functions of time. And that means that you're no longer constrained by that vertical line test stuff. You no longer need to be 1-to-1 in either direction. In general, these can look like anything. right? You could, in theory, again, this is the x-axis, this is the y-axis, there is no t-axis. Your curve could meander all over the place and do whatever the hell it wants. But there's always an initial point, and that's the point associated with the smallest t value. And we think of it as a path that that point walks along. So it has direction until it gets to the terminal point. And here x is x of t, some function of t. Y is y of t, some function of t. And there's no direct relationship between x and y, but you're given a time domain. So the initial point is the point associated with t equals a, and the terminal point is the point associated with t equals b. So this is what we're going to start playing with next week. I will show you how to find tangent lines in this sort of setting. I'll show you how to find areas and arc length in this sort of setting. And it turns out that arc length actually makes more sense in this situation than in the situation that we learned it in first in chapter 8. But that's where I'm going to leave you guys for today. I hope you all have a lovely weekend. Please work hard on that homework. If you need to talk to me about anything, you can come to office hours or make an appointment to talk with me over the weekend. All right. I hope you all have a lovely rest of your day. I will see you on Monday.